Welcome everyone. I will present our work, psc2code, Denoising Code Extraction from Programming Screencasts. Programming screencasts have become a pervasive resource on the internet, which is favored by many developers for learning new programming skills. However, the streaming nature of screencasts limits the choices that developers have for interacting with its content, such as navigating the video and reusing the source code. An intuitive way is to convert the screen images into text using OCR technique, which can be easily searched and indexed and further utilized to build multiple downstream applications. However, we observe three major noises in the extraction process that will dramatically affect the quality of the extracted code. Thus, we built a tool named psc2code with two components: denoising code extraction and enhancing video interaction. Given a programming screencast, psc2code first extracts source code by 3 steps, then enhances video interaction by leveraging the accurately extracted code. Step 1. Valid code frames identification. Since most of the consecutive frames from the programming screencast are nearly the same, and these highly identical frames are of no use for further analysis, we first remove such non-informative frames by measuring the pixel-level dissimilarity using normalized root mean square error. Here, we set the threshold to 0.05. For example, here, frame 2 and frame 3 will be removed because they don't satisfy the threshold, which suggests that they are too similar to the frame 1, while frame 4 will be retained because it contains enough new information. Next, we further remove frames that do not contain code or the contained code is partially visible. Due to the limitation of annotated data, we fine-tune a pre-trained CN model as the classifier. Step 2. Code region extraction. To eliminate interferences from non-code regions such as code completion suggestion window and the pop-up menu, we crop code editor window from valid code frames. To do so, we detect the candidate boundary lines using candy edge detector. However, the original detection results are very noisy. To reduce the detection noise, we carry out 2 steps of clustering. First, we use dbScan to cluster close-by boundary lines based on their overlap and distance. Interestingly, we further cluster frames with similar window layouts. This level of clustering is very helpful since it can effectively eliminate the differences, which is also considered as noise, between detected edge maps of different frames. Finally, we crop the code editor window based on the filtered edge maps. Step 3. OCR Errors Correction. psc2code extracts source code from the cropped code region using Google Vision API. Errors are very common in the original OCR code. For example, cursor is wrongly recognized into letter I. We detect these errors by training statistical language models from a large corpus of source code collected from 300 GitHub Java projects as domain-specific spell checkers. Specifically, we build a unigram language model and a line structure model. To correct the detected errors, we leverage cross-frame information, that is, a wrongly recognized code line in one frame might be correctly recognized in another frame. For example, in frame I, a code line is wrongly recognized into properties prop in minus new properties, whose line structure is. Here, IDU and IDL represent for identifiers start with upper and lower characters. However, in frame J, this code line is correctly recognized. So fixing a detected error code line is pretty straightforward. We match it with correct candidate code lines using added distance and replace it with the matched correct counterpart. By leveraging the accurately extracted code, our interaction-enhanced video player supports following 4 features. Video analysis. psc2code can automatically extract the source code from any programming tutorial on the internet. Search navigate by code. psc2code can search for the specific frame and directly navigate the video based on the input query. Files content view. psc2code provides watchers a clear view of any code content appeared in the screencast. Action timeline. psc2code informs watchers when the tutorial order does what to which file. In the experimental evaluation, we first evaluate the effectiveness of psc2code in denoising code extraction. Then, we conduct a user study to evaluate the applicability of psc2code in enhancing developer interactions with programming screencasts. First, we evaluate the effectiveness of three main steps in denoising code extraction, which are valid code frames identification, code region extraction, and OCR Errors Correction. To build the testing dataset, we collect 23 most popular playlists for Java tutorial from YouTube, and then randomly sample 2 videos from each playlist, which gives us 46 programming tutorials. Finally, there were 4,828 frames involved in the testing. For the formal 2 steps, we use the approach of Alamadi's work as our baseline, where a YOLO network is applied to identify valid code frames and crop the code region simultaneously. Here, we use the metric intersection of a union to measure the accuracy of predicted code region bounding box. In this frame, green bounding box is the annotated ground truth, while the red one is predicted by the model, and the IOU is calculated as dividing the area of overlap between bounding boxes by the area of union. A higher IOU suggests a more accurate predicted bounding box. For OCR Errors Correction, we calculate the ratio of incorrect words that are corrected by psc2code for each frame in the testing set. So now let's ask, how effective is psc2code in identifying valid code frames and locating code region? This table shows the comparison results between psc2code and the baseline. This column is the accuracy for valid frames identification. These 2 columns are F1 scores for identifying valid and invalid frames respectively. The last column shows the IOU for the predicted code region bounding box. Then we ask, how effective is psc2code in correcting OCR errors? The ratio of incorrect and correct words is about 1:3 in the original OCR code, which suggests that OCR errors are very common. 88% of the detected OCR errors can be truly corrected. For those psc2code fails to correct, mostly because there were multiple similar words in the code and psc2code fails to choose the correct one. However, only 46% of all the OCR errors can be truly corrected. This is because our trained spell checker fails to distinguish incorrect words from the correct ones in some circumstances. Next, for evaluating the applicability of psc2code in enhancing developer interaction, we conduct a user study. 3 programming tutorials with different topics are chosen from our dataset, and we design a quiz for each tutorial with 5 questions. To correctly answer these questions, participants must carefully explore the code content, API usage, and other information introduced in the tutorial. 10 participants are randomly divided into 2 groups. Participants in the experimental group use our interaction-enhanced video player, while those in the control group use regular video player. Participants in both groups are asked to answer the same questions and rate the usefulness of the corresponding tool. The ratings are on a 5-point Likert scale, with 5 being the best. So now let's ask, how useful is psc2code in enhancing developer interactions with programming screencasts? This table shows the results of a user study. This column presents time that participants use to finish the questions. This column is the correctness of answers that participants give. The last column shows the usefulness ratings given by the participants. The results suggest that participants genuinely agree that our tool is more helpful for learning knowledge from video tutorials compared to the regular video player, which is also confirmed by the fact that participants in the experimental group do give more correct answers in less time. In conclusion, we explicitly address the 3 noisy challenges in the code extraction process. We develop a tool named psc2code to enhance developer interactions with programming screencasts through accurate code extraction. And that's all. Thanks for your attention.
Morning, good afternoon, good evening, depending on where you are in the planet. Welcome to this image processing session, and we are happy to welcome our speaker, Linfeng Bao, that has presented the paper that you saw in the video. I see that there are questions in the chat. Please let me start with one question. Linfeng, thank you very much for being here. I am Oscar Pastor, professor of the Universidad Politécnica Valencia in Spain, and it's an honor to me to chair this interesting session. So, Linfeng, my first question is going to be about what about code region extraction? Have you identified some sort of universal patterns? When you denoise detected lines, how to assess that you fully detect them correctly and completely?
Okay, thank you for your question, Professor Pastor. And I think for the code region in our study is the boundary in the IDs. We want to detect these boundaries for the code region, and I think there are some patterns for these boundaries. We first detect the lines by some image processing techniques, and then we to denoise this detect lines, we collect some close and similar lines, and to access that we fully detect them correct and completely, we first develop a web interface to show this image and the detect boundaries. And sometimes the boundary is not correct. Then I remember we adjust some parameter in the cluster algorithm, and sometimes the result will be good. But for some case, we cannot detect the boundary, as maybe because this frame or image is not we cannot get a very good result for by our approach. So for such case, maybe it is our approach cannot work very well. And I think for most of frames, our approach can work well.
Okay.
Thank you.
Okay, thank you. There is one interesting question following up this argumentation from Sang Sejun. Thank you. Sang is the question is, how do you fix the errors in the OCR results, and can your approach be applied to other programming languages?
Okay, thank you for this question. And first question, we actually first crawl a large number of GitHub projects, and then we build 2 language models at code token level and the code line level, and then we use this domain specific check to identify the OCR errors. And to fix these OCR errors, we consider some error because we observed that some errors in other some error in our frame that is correctly by our approach in other frames. So we use this classifier and find the most similar one to based on the string edit distance thing. We fix OCR errors.
Okay, thank you. Also Chao Ni is making an interesting comment and question. Great work, he's saying. The question is, why do you use traditional image processing techniques to detect the boundaries of code area, but not the advanced deep learning-based object detection methods?
Okay, thank you for this question. And because the code regions that we want to extract from the program screencast share some universal pattern, and normally the interface of the IDs have similar paths divided by clear boundaries. So for the central and the biggest one is the code region, and then we leverage this heuristic, and our method can detect the code region very eventually and privacy. But due to the correlation and undersampling of a thing and the boundaries detected by the deep learning based method are not very precise. And also this method suffers from poor generality because there are many different IDs, and the IDs maybe have different interface, and moreover, because for this deep learning models, we need spend a lot of time to label samples, so it will cost a lot. And thank you.
Okay, I think that in any case, it is interesting to see that your work is open to incorporate any other technologies as deep learning based one, because the idea is still valid. I think that this is a good point, Ling Feng. Thank you very much. So,
thank you.
Another question is what conceptual patterns do the OCR detected incorrect words follow? Have you been able to conceptually characterize potential incorrect words? Again, something that other people are asking for. Does this depend on what programming environment or technology is used?
Okay, thank you for your question. I think in our study, we didn't find the patterns for OCR detect incorrect words because, as mentioned in the last question answer, we detected the OCR errors based on the language model. So based on this language models, we found some incorrect words, and then to fix them. And for the next the question is, does it depend on what program environment technology is used? I think our approach do not depend on program environment and technology, because our approach is based on the language models. Is not related to program language or other technologies. Okay.
Okay, thank you. It's clear. Thank you for the answer. There is probably time for a last question. That one is related with the experimental design of your reported in your work. Only 3 programming tutorials have been considered in the experimental evaluation for enhancing video interaction. Is it a sufficient number to deal with genericity? Do you think that they are representative enough of the different situations that can be faced in this working domain? Any incomes about this working context?
Okay, thank you for your question. I think the number of programming in our study, I think, must be limited. But because we select 3 typical program tasks, and I think it they are a bit repetitive for some work domain, but it must be not covered all the situations. I think in the future work we can maybe build more program tutorials based on our studies. And thank you.
Okay, so thank you very much. We are almost finishing, only 40 seconds. I think that the work has been really interesting. Thank you everybody for asking your questions. So I remember you that after the end of this session, Q&A session, there is the opportunity to join the author in the discussion room that is assigned to the paper. If you want to take advantage of this opportunity, don't hesitate to do it. And I invite all of you to continue with the next paper that will be on in less than 5 seconds. So thank you very much, and see you in a few minutes. Bye-bye.
Bye-bye.